Hello math analysis students. In this video we are going to continue to learn about hyperbolas. Last class and last video we started learning about hyperbolas. We learned how to graph hyperbolas, and we learned how to write the equations of hyperbolas, and we learned how to find the equations for the asymptotes. And now we're going to talk about the foci of a hyperbola. The idea of a focus point for a hyperbola is very much like the idea of a focus point for an ellipse. For an ellipse, you'll remember that the definition of an ellipse was it's the set of all points where the sum of the distances to two fixed points called the foci is constant, and our ellipse equation has a plus sign in it. For a hyperbola, the definition is the set of all points where the difference, or the absolute value of the difference of the distances from any point to two fixed points, the foci, is constant. And our hyperbola equation has a minus sign in it. We learned last time about finding the center, finding our A and our B values, how to draw the rectangle and draw in our diagonals to extend those to get the asymptotes for how to graph our two parabolas that make up the hyperbola. And foci are key values for that definition. And the foci are found here in exactly the same way that we found them for the ellipse. The foci, when it's a horizontal hyperbola, we find the foci by doing h plus or minus c, k. And when it is a vertical hyperbola, then we find the foci by doing h, k plus or minus c. And we find them the same way because the idea is the same. The distance from our center point to our vertex, this is our A value, and the distance from our center to our foci is our C value. The difference this time is that C is farther away from the center, because it is inside of each little parabola that we have. So our C value is bigger than our A value this time. So it makes sense to use C squared equals A squared plus B squared. This should look very familiar and very similar to the ellipse. But remember, with an ellipse, our ellipse equation has a plus sign in it, and our ABC relationship has a minus. C squared equals A squared minus B squared. For a hyperbola, our hyperbola equation has a minus, and our ABC relationship has a plus. So when we're finding the foci, if it's a horizontal hyperbola, we'll add that C value, add and subtract it to our H, which indicates that from the center, we're going to be going a certain amount left and right. So right is when we add H plus that C value. Left is when we have H minus that C value. And the K value doesn't change. When we have a vertical hyperbola, then we would be going up and down from our center point. So we would have H K plus C, that indicates when we move up from the center, and K minus C indicates when we move down from the center. So let's take a look at this problem that we worked on last class and last video. We have this equation, x minus 1 squared over 25 minus y squared over 9 equals 1. And last time we talked about how to find the center and our A value, A and B values. We drew in our box, drew in our asymptotes, and then drew in our two parabolas that make up our hyperbola. To find the foci, we are going to use, first of all, our A, B, and C values. We know that C squared is equal to A squared plus B squared. And we found our A and our B last time, and we have our A squared and B squared in our equation. So C squared is equal to A squared is 25 plus B squared is 9. So our C squared is 34. So our C value is the square root of 34. And so that is the amount that we're going left and right of our center. And since our center is at 1, 0, then our foci will be at H plus C, K, and h minus c, comma, k. Now, if you were to put these into your calculator to get an approximate value, 1 plus the square root of 34 is about 6.8. So it would be over here. And 1 minus the square root of 34 is about negative 4.8. So over here. And that's how we would find our foci for this horizontal hyperbola. For this vertical hyperbola, we found the center last time, how much we moved left, right, up, and down, drew the rectangle, drew in the diagonals to get the asymptotes so that we could draw the two parabolas that form our hyperbola. And for the foci, we need c value. So once again, c squared equals a squared plus b squared. So c squared equals 16 plus 4. So c squared equals 20. So c is the square root of 20. So our foci will be at h, k plus c, and h, k minus c, which means right here from the center point, which is at 1, negative 1, we'll have 1, and then negative 1, and we'll go up square root of 20 units. And our other focus point is 1, and it's negative 1 minus the square root of 20. And again, if you were to put these into your calculator to get approximate values, negative 1 plus the square root of 20 is about 3.5. So that would be about right here. And negative 1 minus the square root of 20 is about negative 5.5. So that would be in here. It's usually pretty close to the vertex. Just like with our ellipses, it's usually that focus point is pretty close to the vertices there also. Okay, well, let's do a couple where we find the equation of hyperbola from some different pieces of information given to us. In this example, we are given the foci and the vertices, and we want to find the equation. So let's start by plotting. You don't have to have a graph for these, but it's a lot easier to see the distances and what's represented on a graph. So I recommend having a graph. The foci are at 0, negative 3, and 0, 3. Now this tells us some stuff right away. The foci are still on that axis connecting the vertices. Our vertices are at 0, negative 1, and 0, 1. I'll use a different color for that. 0, negative 1, and 0, 1. So we can get a rough idea already of what this hyperbola looked like if we needed to graph it. It is a vertical hyperbola, and the center is at 0, 0. So let's make a note of that. Since the center is at 0, 0, and it is vertical, then we know that our equation is going to be written where we would have the y squared first, y squared over something minus the x squared over something equals 1. And let's see how we get those numbers that go underneath. So the distance from our center to our vertex, this value right here is our a value. And in this case, a equals 1. And the distance from the center to our focus point, that is our c value, and here c equals 3. So we would use our relationship c squared equals a squared plus b squared to solve. C is 3 squared, which is 9, equals a squared is 1, plus b squared. So that means b squared equals 8. So we just need to put those values into our equation. Our a is 1, a squared is 1, and b squared is 8. Let's do another example. Here we're given the center point, 1 focus, and 1 vertex. So here we have our center is at 4, negative 2. That's our center point there. And we have a focus point is at 7, negative 2, and a vertex is at 6, negative 2. So we can tell here that this is going to be a horizontal hyperbola because our vertex and our focus are here. So we've got the center, which is 4, -2, and we know it is horizontal. So we can go ahead and set up our x minus h squared over something minus y plus 2 squared over some number equals 1. And let's figure out that a, b, and c values. So if this point right here is our center at 4, -2, from the center to the vertex, that is our a value, that's 2. And from the center to our focus point, that is our c value, which is 3. So using our relationship, c squared equals a squared plus b squared, we just plug in and solve. C squared is 9, a squared is 4, plus b squared, and that leaves us with b squared equals 5. So we just plug in right here, our a squared is 4, and our b squared here is 5, and that is our equation of our hyperbola. Okay, there's one more big topic we're going to talk about today, which is how to identify conics based on their equations. We know how to put things into standard form, but we can identify what type of conic something is without having to go through all of that just by looking at our x squared and y squared terms. Remember, there are 4 types of conic sections. There's a circle, an ellipse, a hyperbola, and a parabola. Now, we're not discussing parabolas in math analysis because you've done parabolas before. You've done them in Algebra 1, you've done them in Algebra 2, you've worked with parabolas before. And you know that parabolas only have one squared term. They don't have an x squared and a y squared. It's a y equals x squared, or you could have x equals y squared. So the first thing we want to look for is, are both x squared and y squared present? If you only have one squared term, then that's a parabola. Even though we're not discussing how to graph them, one squared term, parabola. But if we have both an x squared and a y squared term, then we want to look at, do they have the same sign? And this is important to note here, that when we're comparing the signs, they have to be on the same side of the equation. If they do not have the same sign, then that's a hyperbola. It'll either be an x squared minus y squared or a y squared minus x squared. But different signs means a hyperbola. If they have the same sign, then we look at the coefficients of the x squared and y squared term to determine if it is a circle or an ellipse. If the x squared and y squared have the same coefficient, then we have a circle. If x squared and y squared have different coefficients, the same sign, but different coefficients, then it's an ellipse. So let's do a few problems just to practice. These 12 problems right here. Number 1, since we have an x squared and a y squared term, they both have the same sign, but they have different coefficients, then this number 1, this problem right here is an ellipse. Number 2, since we have an x squared and a y squared term, they both have the same sign and the same coefficient, we have a circle. Number 3, we do have an x squared and a y squared term, but they have different signs. This is a hyperbola. Number 4, we have x squared and y squared terms. They have the same sign, but different coefficients. That one's an ellipse. Number 5, we do have both squared terms, same sign, same coefficient. That's a circle. Number 6, we have both x squared and y squared, same sign, coefficient. That's another circle. Number 7, we only have one squared term. We have an x squared, but not a y squared. That's a parabola. Number 8, we have an x squared and a y squared, but they have different signs. The x squared is positive, the y squared is negative. That is a hyperbola. Number 9, we have an x squared and a y squared. Same sign, but different coefficients. That's an ellipse. Number 10, we only have one squared term, so that one is a parabola. Number 11, we only have one squared term, so that is a parabola. Number 12, we have an x squared term and a y squared term, but they're on different sides of the equation. If we were to move them to get them on the same side of the equation, then they would have different signs. One will be positive and one will be negative, so that indicates that we have a hyperbola. And that is how we can tell the difference between our conic sections without having to actually get them into standard form. All right, thanks.